Good afternoon, friends. So, I think we can start now. So, this week's lectures have covered about flexible link manipulators. So, basically, till now, what we have seen are systems where the links are rigid and they do not deform. But now we have seen systems where the links can also deform while moving. So, that gives rise to a whole new way of analyzing the motion of these manipulators. And we have seen how to do the kinematics and dynamics of these systems, and some different types of cases that could arise in these kind of systems. So mostly all the questions are based on the kinematics, dynamics, and control of these flexible manipulators. So for the first question, which asks what are the two generalized coordinates associated with a flexible link, right? So we can start with a discussion, a brief recap of how exactly do we represent a system of flexible links interconnected via revolute joints, basically. So let me just draw a flexible manipulator. So this is the first link, this is the joint, and this is the second link, right? So what we have is, first we assign frames. So the first frame we assign is tangential to the base of the first link, and similarly we assign a frame tangential to the base of the second link, and finally we have a frame assigned at the end effector, right? So we can mark certain quantities which are useful. So let's first name the frames. This is x0, y0, y1, x1, y2, x2, y3, x3, right? And this is the angle that the first link makes. So this is θ1, this is θ2, and this is what we call as the deflection, basically. So you can imagine that, let's say if this were a rigid link, right? So if it was a rigid link, then the slope would not change as we move across the link, right? So the entire link would be at θ1, but since this is a flexible link, so there is a deflection from that x1 axis, basically, and the deflection, the actual length varies, as you can imagine, varies depending on the point at which we are trying to compute that deflection. So that deflection is also not constant. The deflection is less closer to the base and more away from the base, right? So this deflection is denoted by W1 and is a function of x1. So basically, first let's write the frames. So x0, y0, and this is the base frame, x1, y1. So these two make up the link 1. And x2, y2, and x3, y3. This is link 2, right? So for each link, what are the quantities do we need to describe that link for each link? In rigid case, we just needed the angles, right? We just needed theta i's, the angle that a certain link makes with the preceding link. But here we have theta I, and which is a joint angle, right? And wi xi, which is the basically deflection. Right? And this is joint angle. So we need these two generalized coordinates for each link. So two generalized coordinates for each link. And as I told, so the deflection in the ith link varies according to the position of the point of interest. Xi is the position of the point of interest where we want to compute the deflection. Right, and so xi, the value of xi would vary from 0 to the length of the link. Where li is length of the link, right? So once we know these two quantities, we can write the position of any point on the link, right? So position of any point on the link, and this is given in which frame? So you would imagine in this x1 y1 frame, let's say for this point, so what will the coordinates? It will be xi, since we are looking along this red axis, right? So xi, and this is the y coordinate, so wi. So the position of any point on the link in frame xi yi. this you have to note that in which frame we are writing that position, right? It's a frame dependent quantity. So pi is dependent on xi, and it's given by xi itself and some function of xi. It's the deflection. Right. Similarly, we can write other kinematical quantities and proceed with the kinematical analysis of the system. For instance, like the rotation matrix you can write. So rotation matrix of link I will be given by same as this would be same as before. So cos theta I minus sin theta I cos theta I, right? And so you can proceed with the remaining analysis. You can refer the lecture for that. Okay. So now we come upon the boundary conditions that can arise or that we have studied in the lectures in case of these flexible links. So we have seen pinned joint, pinned links. So basically combination of any two of these three. So pinned fixed, like that, fixed free, right? So pinned means that it's connected with a revolute joint basically, so it's free to rotate in a plane. So something like this is a pinned joint where you can rotate about this joint, the usual revolute joint that you have seen, right? And fixed is when you don't have any motion at this end, right? This is fixed. So basically you can write this is pinned and this is free. So this is a pinned free. Now this would be fixed and free, right? So another case would be like free, this would be free. It could be like fixed. So depending on these boundary conditions, basically how the beam will deform changes, right? This is fixed. If you have studied, some strengths of material courses, mechanics of solids courses, there you would have seen these kind of things, like how different boundary conditions give rise to different kind of deflections in beams. So yeah, okay, moving on to the next question, which talks about the control of these manipulators, right? So I will start with, like, basically when we are doing dynamics, I think we have discussed it before also, there come up two terms. One is inverse dynamics and one is forward dynamics, right? So inverse dynamics and forward dynamics. So in inverse dynamics, what do we know and what do we want to compute. Basically, these two differ in the on these aspects. So inverse dynamics, we know the accelerations, and the velocities and all. So all these we know, and we want to compute the desired forces, torques, right? And in forward dynamics is the reverse of this. We know the forces or torques, and we want to know how the system will respond. Basically, accelerations and velocities and position in turn. So, right, so forward dynamics you would use while finding, you're trying to, the commands, the torques that you're commanding. So you want to know the trajectory of the manipulator. So you would do forward dynamics. And inverse dynamics you generally use while developing the control laws, because you know that, okay, this is the desired trajectory, you want to track it. So what would be the required torque to track this trajectory? So there you use the inverse dynamics, right? So we are doing something like this only. So this expression you would see is, what are we computing? We are computing basically, if you see all these three expressions, they are expressions of joint accelerations, right? So basically we are doing forward dynamics. So in general, the equation of motion of a multi-body system is given by, I think you would be familiar with this equation at this point. Right, so it is given by tau, which is the torque, is, I will first write the equation and then describe what each term means. I will try to be consistent with the notation used in the lectures. So just okay. So right. So this is the form that you would generally come across. So let's start with tau. So tau is, n cross 1 vector, and here n would be the number of actuated joints that you have, because those are the joints where you would be applying the torque, right? Now this is the joint space inertia matrix of the system. What is this? Joint space inertia matrix, right? So this is a symmetric positive definite, basically your mass matrix. So this is positive definite matrix. So n cross n, these are the joint accelerations, n cross 1 vector. This is your centrifugal and Coriolis matrix, basically the effect of these forces on the system. Again, these are joint velocities. And these are gravity terms. Right. So in case we also have some frictional effects, so we can add a friction term also, right? Generally it's not written, but since it's there in the lectures, I will just put it here, right? So this is friction. Okay. So let's say we know, so what in forward dynamics we know the torques, and we have to compute this theta double dot, right? So basically you would take these two terms to the left hand side and then multiply it with the inverse of in the inertia matrix, right? That would give you theta double dot, and that is basically what is being done here also, right? So basically just you can rewrite this equation so that theta dot is the only theta double dot is the only term on one side, so that will be theta double dot is equal to m inverse tau minus v theta dot minus g theta, right? And if you would see, this option B corresponds to this expression, right? Now since there's a term here, dynamic model based control, right? Dynamic model based control, so let's just briefly cover that also. Right. So what we do is we say that let's write the commanded torque as alpha times tau dash plus beta. And what are these alpha and beta and tau dash? So alpha is the joint space inertia matrix, right? Beta is the Coriolis and centrifugal term, basically the remaining terms, the gravity and friction and all, right? And tau dash is basically your desired accelerations plus a PD law, basically, which again you have seen in earlier control laws also. So kV times E dot plus Kp times E, where E is theta desired minus the actual. So the subscript D denotes desired, right? Theta D is desired joint angles. Okay, so let's put these values of alpha, beta and tau dash in this expression, and we will compute the LHS and RHS separately. Right. So let's first simplify the RHS by substituting all these values. So RHS alpha is m I will drop these dependencies on theta and theta dot for just trying to be brief. So m times tau dash kve dot plus kpe plus beta. Beta is v theta dot plus g plus f, right? So if we expand this, what will we get? M theta double dot d plus v theta dot plus g plus f, right? Just try to see. And on the LHS, we have the expression for tau, right? So it will be m theta double dot, basically the usual expression of tau that we wrote here. Pintu, do you want to ask something? Please mute your microphone. Okay, so plus g plus f, right? And so if we equate the LHS and RHS, oh, I missed some terms here. kv e dot plus kpe m times, let me rewrite. Yeah, so plus m times kv e dot plus m times kpe. Right, so equating LHS and RHS, what we will get? So m theta double dot plus v theta dot plus g plus f is equal to m theta d double dot plus v theta plus g plus f plus m kv e dot plus m kpe. Right, so few terms would cancel out. All these three terms would cancel out. And if we take m theta double dot onto this side, onto the right hand side, what we will get is m times theta d minus theta double dot plus m kv e dot plus m kp e is equal to 0, right? So, and again, this theta double dot d minus theta double dot is nothing but e double dot, right? So e double dot, and m is there in all the terms, so we can cancel it out. So finally we get e double dot kv e dot plus kp e is equal to 0. This is our air equation. This is error equation, right? And since these kv and kp are diagonal matrices, basically we can write these as separable equations for each of the ith generalized coordinates, basically. So what I try to say is that, like, let's say for a 2 degree of freedom system, what would this equation look like? So theta vector would be theta 1 theta 2, right? So similarly the error vector would be e1 e2, right? So this expression would look like something this: e1 dot e2 dot double dot, sorry, and kv is a diagonal matrix, so kv1 0 0 kv2, then e1 dot e2 dot plus kp1 0 0 kp2 and e1 e2 is equal to 0 0, right? So whenever the coefficients in such an equation are diagonal matrices, then we can basically write separable equations in just which equations which have just variables for single degree of freedom, right? So basically we can separate. If you multiply these matrices, then what we will get separate equations in terms of e1 and its derivatives and e2 and its derivatives. There will be no coupled terms, basically, right? So that's the advantage of having diagonal matrices as coefficients. So basically in general we can write this as ei double dot. So you would find that in this equation e dot and e double dot are vectors and kv and kp are matrices. So these would be n cross 1 vectors, and these would be n cross n matrices. When we write them separately, then it's just a scalar equation. So ei double dot plus some number kvi ei dot plus kp I e equal to 0, right? So this is a scalar equation. And the result that we have derived here would give us the answer to one of the questions of the assignment, which is this, right? So the second order error dynamic equation for the dynamic model based control of a robotic system is this, which we have just derived. So I will just put a note here, derived in question 3. I think it was 3. Yeah, right. Okay. And question 4 is again would seem very familiar to you because we did exactly this in the last week's discussion hour, the closed loop inverse kinematics algorithm and its error dynamics. So I would just quickly repeat the relevant equations. So basically what we are trying to do, we are trying to compute the joint angles not using yeah, so basically what we define here is basically we don't want to compute individual joint angles. So E we define as xd minus x. That's again the desired motion of the end effector and the actual motion of the end effector, right? And q dot would be q. So we know that this relation holds, right? That x dot is j times q dot. Okay, and E dot is xd dot minus x dot. So what we describe x dot as xd dot plus k times E, right? This is sort of our one relation. Basically what are we doing? We are so the actual velocities, how are we computing that? We compute the desired velocities and we compute what is the error in the current error in the positions, and we apply an appropriate feedback on that and we add it to the velocity term. So basically this is a proportional correction only. There is no D term here, this is only P control, right? So in this equation what putting this here will give xd dot plus ke is equal to jq dot, right? So q dot is equal to j inverse xd dot plus ke, right? and if you write x dot is equal to e dot, so x from this equation we write x dot is equal to minus e dot plus x d dot, right? And x dot, and from this equation what we have x dot is equal to x d dot plus ke. So on comparing these two, what we have, e dot plus ke is equal to 0, right? So this is the first order. Error dynamic equation, right? And the block diagram and all, you would have already seen in previous slides also, and this week's slides also. Okay. Next question. Robot kinematics is the study of dash without consideration of forces associated with it. This is a very fundamental question. So basically in kinematics we study about the motion of a body without actually caring about what is actually causing that motion, right? So just we study the motion. So this is the right answer, motion. And in kinetics, so two terms that form the fundamental of dynamics basically. So kinematics and kinetics. Kinematics only motion, and here we study about the agent causing the motion. We consider that also. So in very crude terms, this is the study of motion. This is study of motion plus forces, all kind of forces. This is kinetics. Kinematics. Right. Sixth question, we just derived the second order aerodynamic equation. So this is done. Now coming on to the seventh question, which is concerned about the kinematic modeling of flexible link manipulators, and the approach discussed in the lecture slides is basically what we call as the assumed modes approach. So since here we have to just choose the name, so this is obvious, but let's briefly see what are the things that are involved in this assumed modes method. So assumed mode method, like basically this requires some background of beam theory and all. So I guess you would have heard about this Euler Bernoulli equations for beams, right? So in this assumed mode method, what we have, right? So assumed mode method, what we have is a finite dimensional model of order mi of link flexibility right. And so basically we are trying to figure out how will these flexible links deform as they move, right? So the dependence of deflection on space and time, basically. So the Euler-Bernoulli equation looks something like this. So for each link, right, subscript I denotes that the quantities are for the ith link. So EI, I will write the equation first and then explain the terms in the equations. So right. So what are these terms? So this first term here is what we call as the flexural rigidity, a very common term appearing in deflection of beams. So flexural rigidity, basically it is something, a quantity which signifies how easy or difficult it is to deform a beam, basically, right? So if the EI value is high, it will bend less easily, it's harder to bend, and if EI is less, it is easier to bend. Wi is the same as before, it's the deflection, and it depends both on space and time, basically position of the point and time, because the deflection is not constant throughout the motion of the link, right? And it's the partial derivative of the deflection with respect to the position and the fourth order partial derivative. This is the density of the link, and we assume that this is uniform, so there is no dependence on space or time. Uniform density. And again, the second term is the second order partial derivative of the deflection with respect to time, right? And these deflections we can also write as Wi xit is equal to J is equal to 1 to mi Wij, 1 to mi right. So we there are like there's a new variable here, tij, right? So what is this? So this is a time varying variable and these are the assumed mode shapes of the link. Mode shapes, I'm not sure if you are familiar with this term mode shapes or not, and we can't go into depth of that here, but it's something like the different, basically you would imagine that there are different ways in which a beam can deform basically, right? So like it could be possible that, let's say there is a fixed, so it could be possible that it just deforms like this, right? The nodes are at both the ends, and it could be also possible that it deforms something like this, right? So these like different kind of actual shapes of deflection, these are called mode shapes. So roughly what we are trying to do is that we are trying to compute the deflection by summing up different mode shapes and multiplying them with certain coefficients and adding them up to figure out the actual deflection of the flexible links. And for solving these equations we need some boundary conditions, right? Right. So, and before that, this variable t, right, this variable t, this has a form like this: a cos omega nt plus b sin omega nt, and omega n is equal to bn square ei by rho. Yeah, and boundary conditions, which are very, very important. So at the base of the link, the deflection is 0, right? At the end of the link, this is, I guess, for the fixed case. At the end, the deflection is also 0, and the derivatives are also 0. So these boundary conditions would depend on, whether it is pinned, it is fixed, or it is free. They depend on that, right? So this would be one for fixed case. So this it is not that it's same every time. It depends on whether it is fixed pin or what was the third one? Free, right? Okay, so the next is a more sort of implementation type question. What is the MATLAB command used for differentiating an expression with respect to a single variable? So if you would know this from before, it's the diff command, and I would just quickly show you an implementation of this function. So this is the online MATLAB command window. So basically, what does the diff function do? If we input a symbolic function, it differentiates, and let's say we say which variable to differentiate with respect to, and we can also give like what would be the order of the differentiation. So let me just demonstrate it. So first, let's take a single variable function. So first we define a symbolic variable. Let's define two of them. Right. Now let's define the first function f1 as sine of x square. Right. So now let's compute the first differential of this function. So we will use the diff function, and the first input would be the function which we want to differentiate. Second argument would be the variable with respect to which variable we want to differentiate. So here there is only one variable, so x, and third would be the order of differentiation. So let's find the first order differentiation, and you would see 2x cos x square, and you would just by inspection you can verify that this is correct. Like the differentiation of sine x square with respect to x is 2x cos x square. And similarly you can compute, like let's say if I want to compute second order differential, right? So you can compute that also. You can try this out and you would see that this is correct. In fact, obviously you can compute any order of differentials, right? So very useful. And let's say we have a function which has multiple variables, right? So let's write something like sine x plus sine y, right? And now let's check this df2 with respect to x. Diff, we want to differentiate f2. Let's first differentiate with respect to x and the first order. So this is cos x, which you would expect. Basically you are doing a partial derivative with respect to x of this function, right? And if you put y here, it will differentiate with respect to y, right, which is cos y. So, and similarly here also, let's say you want to find out the third order partial derivative with respect to y, which is minus cos y, right? And you can give as complicated functions. So let's try one more. Let's modify this example itself. Let's put like y into sin x and x into sin y, right? And then right, with respect to x, second order partial derivative. And similarly, if we want to do with respect to y, so right, so a useful function to compute derivatives of expressions. Basically, you would also find a similar function diff, which actually does something else also. Like there are functions with the same name which do different things. So in that case, let me demonstrate that also. So that diff is basically used to compute the element-wise difference. The difference between the adjacent elements of an array, basically. So let me just show you 1, 2, 3, 4, 5, like, or put some other values. Right, this is x, and if I do diff x, so what does it do? So the first term would be a difference between the second term of the, basically subtract the first term of the original array from the second term. So 12 minus 1 will be the first term here. Then again 3 minus 12 minus 9, 14 minus 3 11, and 5 minus 14 minus 9. Right. So, and as you would expect, if the original array has 5 elements, then the diff of that would have 4 elements only, so 1 less. And if I again do diff of this one, right, so again this would have 3 elements. So each time you do a diff, 1 element would reduce. So this is useful, when let's say you have position data at some 100 time instants, right? Position of a, let's say, point mass at 100 different time instants, equally spaced time instants, and you want to compute the velocity from that numerically. So we can just do diff of that position array and divide by the time difference of each time step, basically divide by the time step, and that would be a velocity, basically. So yeah, these are like few useful functions. And next is how DH parameter based forward kinematics equation be verified. So the obvious way to verify the forward kinematics equation is to give the actual joint inputs, basically give joint angles and see if we are getting the correct positions or not. So forward kinematics is basically, let's just recall once again, forward kinematics. We know angles and we compute the position of end effector, right? And in inverse kinematics, we know the position of the end effector and we compute the joint angles, theta is, right? And the last question for today is, the main problem associated with the inverse kinematic approach is the existence of multiple solutions. So how you can think about this is that let's say their system some like this. So this is a fixed base, and basically there is a two link sort of a, let's say, a leg type thing here, right? This is the end effector. So this is a two degree of freedom system. Now let's say I keep this is the floor, let's say. So let's say I keep the foot fixed here, right? The foot stays here only. But what does this multiple solutions mean is that the joint angles are not unique. Basically, there exists more than one configuration in which the end effector is at the same position but the joint angles are different, which you would imagine, be something like this also. Let me draw it once again. So it could very well be like this also, right? So we can make the end effector reach the same point but in different configurations. The manipulator is in different configurations. So this is like demonstrates multiple solutions. So like in this case, if this is theta 1, then second case this is theta 1, like, which is different. In first case this is theta 2, but in second case this is theta 2. So multiple configurations can lead to the same end effector position, right? Okay, so I guess we covered all the questions, and the questions on in your current assignment is, I guess they are more or less same as these questions only. So now you would be able to solve them easily. Yeah, so if there are any doubts you can ask, or else we can wrap up.
Hello, sir.
Josh, are you saying something?
Yes, sir.
Yeah.
Sir, this is with regard to assignment number 7, in which it is asked, is the following an advantage of sliding mode control? But there is no statement after that. It's assignment 7, question 1 minute, sir. Question number 8.
Assignment 7. Let me just open it.
Sir, current, yeah.
Which question?
Sir, 8. Question 8.
Okay, is the following an advantage of sliding mode control? False true. Oh, I think this is
the
this is a
statement is
mistake.
missing. Yes,
Yeah, statement missing.
statement missing.
Maybe you can again. I don't think I can help with this one. So
Okay,
this
but
seems to-
there should be some statement so that.
Yeah. Obviously.
So shall I put it in that group, or will I get the reply?
Yes, you can try. I guess that's the only way you can try to resolve this.
Okay, fine.
Yeah.
Hello, sir. Amrit, hello.
Yeah.
This is the last assignment. The 8th week is the last assignment, or still it will continue.
It seems like this is the last assignment, but there are still 2 weeks remaining in the course duration, I guess.
Okay, sir. Then one more question. How about the final examination? Will we get the similar questions as in the assignment, or quite difficult?
I'm not exactly sure about that, but
Okay.
I don't think there would be like a very, very big jump in the difficulty level of the questions.
Okay. Because in the first 3 weeks, questions are very tough. It's quite difficult to solve. After attending your session, only we able to solve the questions. But we alone cannot solve the questions. That's
Yeah.
why I'm asking.
Yeah, so what we can do is that I guess so 2 more sessions I would take. So in that maybe we can, or you can come up, bring some questions and we
Okay.
can discuss that also.
Okay, sir. Okay. So coming week also, you will conduct this same session, the sessions
Yes,
like
yes,
this.
yes. I
Oh,
will do the session.
okay. That will be helpful for us. Thank you, Amrit. Thank you.
Thanks.
Thank you, sir. Thank you, sir.
Okay, then see you next week. Bye.
Yes.